This is Charles. In this video, we will be looking at post-processing for the turbomachinery simulation using Fluent. Right now, let's look at the residuals. As you can see, it stopped descending and start to fluctuating roughly between 200 and 600. And if you look at the uh, mass flow, it's still fluctuating. And if you look at the pressure ratio, it's fluctuating. The efficiency is rather stable. I would say this is not acceptable for the final simulation. For example, when we are doing the performance map. But this is good enough for a preliminary design simulation. Let's talk about why. The first is when you're simulating fluids, maybe there isn't a stable state. Maybe there is only a transient solution. So that the residuals can be fundamentally not zero based on your case. The second is that if you look at some graphs, for example, let's see the total pressure graph. As you can see, it's giving you a uh, pretty reasonable result. Um, so you can use this result to guide your uh, future designs. And actually, if you look at it carefully enough, for example, if we view the velocity triangle, actually, if you look at the console log, you'll see that there is reverse flow for the like 1/5 of the pressure outlet area. Apparently, this is not what we want. But if you look at the velocity vectors, you'll see this is actually gives you a very reasonable um, reason or very reasonable simulation. So if you look at here, you'll see that's where the velocity, uh, reverse flow velocity is coming. Um, and that is caused by the flow separation at the diffuser blade. So that this area's pressure is fundamentally lower than the outlet boundary condition. That's why the reverse flow. So that's why you're not getting a low residual, and also the other stuff are fluctuating. Um, so now let's look at this result. I would say there are quite a few places that you can improve. The first is the huge flow separation here. It's creating this recirculation zone near the end. This huge recirculation zone here. That's where your efficiency is dropped. That's where your entropy increase. So that should be taken care of. And also, if you look at the leading edge, there is a huge shock wave here at the leading edge of the diffuser blade. So that needs to be taken care of as well. And let's look at the impeller blade. Impeller blade, right here, there is a velocity region that's suspiciously high. Uh, for that, we might need to take care of, which means the leading edge of the impeller might need to change. And if we look at down there, okay. So now this velocity triangle is showing you the absolute velocity. But for the impeller, we mostly care about the relative velocity. So change that vectors of relative velocity. Okay, colored by velocity magnitude. Let's do relative velocity magnitude. And let's recompute. Okay, it's still giving us this. I need to double check the simulation setting. But if this is the case, I would say there is a huge flow drag that's flow drifting that we need to improve. Cool. So that's how you can use this result to guide your future design. And just remember the turbo workflow gave us generated us some reports so that we can view them here. Uh, sorry, this is wrong. It's here. You can get efficiency. For example, we are using the inlet. It's the rotor inlet, and the outlet is this outlet. Well, let's calculate, say, polytropic, and this is a compression. And if you compute, it will give you a polytropic efficiency of 81 something percent. And you can also do like a volume integral or a surface integral to calculate, for example, force or the inlet-outlet mass flow. So there's a lot that you can do, and it's going to be very helpful. Another thing to notice is that you can absolutely export the simulation data and then use that in the safety post, which in the workbench, that's the result section of the, where is it? That's this. You can export the simulation data, put it in the safety post, and then you can do post-processing the same way as you were doing in CFX workflow. That's all for this video. Uh, Good luck simulating.